now we're going to do example number 4, and now we have kind of a more difficult situation where we've got to use one of our derived formulas. And maybe this is a good time to do that. Time permitting. We have, in our upper left-hand corner, we have PIE. In our upper right-hand corner, we have EIR, just like on your 3x5 card. And we're going to use this E, which is I times R, right? And if we plug that in over here, we wind up with no E in it at all. We wind up with P is equal to I times R, which is equal to I squared R. We'll take out all this. I didn't even touch the board that did that. Okay. I wonder. Nope. All right. So P is equal to I squared R. That's one of our derived formulas. Let's derive our other formula, and we'll select the I, which is green here. We'll select the I, and the I over here is equal to what? E over R, right? So let's take this I, and we're going to stick it in here, and we wind up with P is equal to E times E over R. And we get, from that we get P is equal to E squared over R. And that's our other derived formula. So P is equal to E squared over R, and P is equal to I squared R are our two derived formulas, and we can use those anywhere we like. And they come right from your Pioneer wheel, so still the only rules you need to remember are Pioneer and the two derived formulas you can get from that by substituting this E or this I over here. So now you can always remember those, right? Okay, let's put one of them to work. In this example, we have a resistance total of 1100 ohms. We have in resistor 1, we only know that it has 200 ohms. In resistor 2, we know that it's dissipating 5.4 watts. In resistor 3, we know that it has 300 ohms. In resistor 4, we have 300 ohms. What's wrong with the way they've laid this out, the way Mr. Herman has laid this out for us? We would not write it this way. We would write P on the top, P-E-I-R. So remember, if we're going down, we divide. If we're going up, we multiply. Okay, if we always write it P-E-I-R, if we're going up, we multiply. If we're going down, we divide. And that's why we write it that way. And that's why you're always going to write it that way. You're always going to write P-E-I-R for the totals, P-E-I-R for 1, 2, 3, and 4. And if you do it that way every time, it will simplify doing the problems. Now, let's look at this and find out, what do we know? First of all, we know that R2, where do we get R2? We have the resistance total minus R1, 2, and 4 will give us resistor 2, because if we add resistor 1, 2, 3, and 4 together, we have resistance total. So if we subtract the resistance total, which we do have, 1100 minus R1, 2 plus 4. So if we add 1, 2, we don't know 2, 1 plus 3 and 4, we have 660 plus 200, so that's 860. 860 minus 1100 is 240, is that correct? Okay, so we find our resistor 2 by subtracting the ones we know from the total. So we found that. Now we have two things in one column, two things in one resistor. We have the power, which should be, in my opinion, up here at the top, but we're not going to worry about that for the moment. And we have the resistance. Since we have power and resistance, that's the only thing we know. We've got to use one of our derived formulas. And we're going to use P is equal to I squared R. Because we have the power, And we have the resistance, and the thing we most value is the current, right? So let's use P is equal to I squared R. So let's just plug in the things we know. And we could find that the power, if we divide 5.4, wait a minute, by, now I do this a little bit differently than Mr. Herman, and so I put it here on the board. Since we have P is equal to I squared R, we're going to plug in, and 5.4 is equal to I squared times 240. If we divide 240 by both sides, we get 5.4 divided by 240 gives us I squared, right? Well, 5.4 divided by 240 is 0.0225, and that is not I. That is I squared. So we take the square root of I squared, we get I, right? So if we take the square root of 0.0225, we actually get a larger number, 0.15. And if you check it with your calculator, 0.15 squared gives us 0.0225, right? Okay, so we find that the current is 0.15 amps. So now we can go around and plug that in everywhere. So now that we have that plugged in, we have two things at least in every subtotal. Totals, current, resistor 1, resistor 2, resistor 3, and resistor 4. So now we can start finding things, and we know the current is constant. So now let's find E1. Since we have 150 milliamps, we can multiply up and get 30 volts. That's our voltage drop across. And then if we multiply I times E, 0.15 times 30, we get 4.5 watts is being dissipated across resistor 1. Let's go over to our totals, and we see that we have a total current of 0.15 amps and a total resistance. If we multiply it up, that'll give us our voltage drop, and that means that we have 0.15 times 1100 is what? Okay, so we see that 1100 times 0.15 is 165 volts. And 165 volts times 0.15 will give us our total power, which is 24.25 watts. Now we found everything in resistor 1, right? Let's go to resistor 2. We have 3 out of 4 things. All we have to do is multiply the current times the voltage to get the resistance times our current to get our voltage, which is 240 times 0.15 will give us 36 volts. Down in resistor 3, we have 0.15 at 300 ohms. We multiply those together, we get 45 volts. We multiply 45 volts times 0.15, our current. We'll find that the power is 6.75 watts. And in our last one, we have 0.15 amps and 360 ohms. We multiply those together, we get 54 volts. We multiply 54 volts times 0.15. We'll find that we'll have 8.1 watts. Now, we can add up. What was our original problem? Where's our cross-check here? Were we given all the resistances? We were not, were we? So we could add up our resistances. 200 plus 240 plus 360 plus 300. Is that 1100? Okay, let's do one more. What else could we check? We could check the voltage drops. 54, 45, 36, and 30. Add those together, does that up to 165? 30, 66, 110, 120, 155, 165. Comes out correct, I believe. Okay. So, there we go. That's example number 3. We have one more example.
Number 5.
That was number 4. What did I say?
You said number 3.
Oh, thank you very much. That was example number 4. Let's do number 5. We have one more problem. And in this example, we have a resistance total and a power total. And we have a voltage for resistor 1 a resistance for resistor 2 of 10,000 ohms. We have voltage drop across resistor 1 is 25 volts. Resistor 3, the only thing we know about it is it's going to dissipate 500 milliwatts or 0.5 watts. And resistor 4, we know that the voltage drop across it is 75 volts. However, are we going to find anything with just that little bit of information? Well, we know that current is voltage divided by resistance, and we have those two totals over here. We have voltage total and we have the resistance total, right? So we can divide that, we find our 5 milliamps, which is 0.005 amps, and 0.005 times, or I should say 25 divided by 0.005 will give us the resistance for resistor 1. On our resistor 2, we could multiply 10,000 times 0.005 to find our voltage drop. Across resistor 3, we have current and power. Oh, we're going to have to use P is equal to I squared R possibly. And in our other one, we have voltage and current, so we can use E, I, and R to find our resistance. Okay. We can find our resistance 1 by dividing the voltage by the current. We divide 25 by 0.005, we'll get 5,000, right? 5 into 25 is 5, right? So it's a multiple of 5. Okay. And then if we multiply E times I, 25 times 0.005, we'll find that we only have 0.125 watts of power being dissipated by resistor 1. 0.125. So let's look at resistor 2. I think that's what we're going to do next. Yep. We're going to multiply up 0.005 times 10,000. Now here's a good example. It's 5 times 10 to the minus third, right? Times 10 times 10 to the third, right? 10,000. This is 1,000. This is the minus third. This and this drop out, and we get 5 times 10, a lot easier to do, 50 volts. That's a nice example of how our engineering notation works to make it simpler to do our work. Let's go down to the next one. And we get, well, how did we get that? We find that the voltage is power divided by the voltage, by the current, I'm sorry, PIE. Nice simple formula. We have P and we have I. So we have the current, we have the power, so we can divide the power by the current, and that will give us the voltage. So the power is 0.05 divided by 0.005. Let's write that in engineering notation real quick. Okay. We have, now I'm confused. Let's see. We have P is 5 times 10 to the minus third. And we're going to divide that by, do what? All right, so I started to get this thing wrong and put the power in the wrong thing, but it's 500 milliwatts. So we're going to have 500 times 10 to the minus 3, and we're going to divide by 5 times 10 to the minus third, which is 5 milliwatts, right? Now we can turn that into 500, I think. Divided by 5. And we're going to take this 10 to the minus 3 and we're going to bring it up here, and that makes it 10 to the 6th. 10 to the minus 3 becomes 10 to the third up here. So these 10 to the minus 3 and 10 to the third is going to drop out. We just have 500 divided by 5, which even I can figure out is 100. And if that come out wrong, I'd be really embarrassed. It's happened, but I'd be really embarrassed again anyway. All right, let's stop now.